Welcome back to multivariate calculus. In this video, we're going to be looking at vectors in two dimensions, vectors in the plane. I know from experience that most students who are taking multivariate calculus are currently taking a physics course or perhaps just recently finished their last physics course. And in physics classes, you tend to spend a lot of time talking about vectors. But if you are not taking physics classes and you're taking calculus for other reasons, it may be that it's been over a year since the last time you've thought about vectors. So a quick reminder rehash of some of the basic ideas there. The idea here is to think about extending your idea of a quantity. A quantity is some measurable result. If the only thing you are measuring is a magnitude, then we can call that measurement a scalar measurement. Time and temperature are the most common scalar measurements in physics. Most everything else in physics can be treated as a vector. In a vector, you look at a magnitude and a direction. So for example, a displacement. I walked 5 miles is an interesting fact. It means you got some exercise, but I walked 5 miles north and then 3 miles south is a path of movement. And if I know where you started, I know exactly where you are now. So speed, velocity, I'm sorry, not speed, your displacement, your velocity, your acceleration, forces are generally given as vectors. Something is pushing on an object in a particular direction. Um, and so there are a number of different places where thinking about vector values is appropriate. Of course, this is not physics class, this is math class, so we have to completely abstract away all of those actually useful things and just talk about a scalar and an ordered pair are points on a number line or on a coordinate plane. And a vector, if I get my head out of the way, come on, there we go. A vector is the path from the origin to the point in question. And there are several different ways you can talk about a vector. The one that you most likely saw in your trigonometry or pre-calculus coursework is these angle brackets AB. So the vector with components A and B is the vector from the point 0, 0 to the point AB. And there's a lot of vagueness. And for anyone who has already taken or is planning to go on to take in the future a course in linear algebra, understanding the specific difference and value of a vector versus a coordinate and all of the nuance of there is something that you'll see in that class. But for right now, I'm just going to stick with the picture, right? AB in parentheses is a point on the plane. It's a location. AB in angle brackets is the path from the origin to that point. So if you want to talk about where you are, you use ordered pairs. If you want to talk about how to get there, you use vectors. And once you start talking about how to get there, that means that you can get to do several other different kinds of operations. But before I get into other kinds of operations, let's slow down a little bit. A vector is defined as something that has a magnitude and a direction. The magnitude of a vector is given by this set of symbols. It looks like absolute value bars, but there are two of them. If you've had me for trigonometry, I just use single absolute value bars there. But at this point, I want to start differentiating. Magnitude of a vector is a generalization of an idea called a norm. And if you're going onward in mathematics, the norm gets generalized quite a bit. So thinking about the norm of a vector as the operation which calculates its magnitude. Right? Magnitude also we can think of as the length. How far is it from 0, 0 to AB? Well, using the distance formula, that's going to be the square root of a minus 0 squared plus b minus 0 squared. And we get that the magnitude of our vector is simply the square root of the squares of the coordinates, a squared plus b squared. And then we want to talk about the direction of the vector. And the easiest way to talk about the direction of a vector is to think about the angle in standard position. And to figure that out, what that angle is, we can always just drop down a perpendicular line here. Realize that we've got a right triangle with sides of length A and B, which means that we can just write that the tangent of theta is B over A. These should look incredibly familiar to you. Going from the components of a vector to the magnitude and direction angle is exactly the same as going from rectangular coordinates to polar coordinates. It is the exact same calculation. And so with that picture in mind, you can think about a vector as being in component form, as being in rectangular coordinates, or being in polar form with magnitude and direction. And as you saw when we talked about polar coordinates, they are definitely more challenging to work with. And that's the reason that when we're trying to actually do work with vectors, we almost always want them in component form. Although even looking at component form can be a little bit of an annoyance from time to time. All right, and for that reason, it's very convenient to have some unit vectors. A unit vector is any vector E such that the norm of the vector is 1. And to make it obvious that we have a unit vector, very often we're going to use a decoration of a hat instead of the over arrow that we most often use for vectors. Before I get any further, I want to at least mention that my background, my training as an undergraduate was as a physics major, not as a math major. And so I've picked up some very bad habits that physicists like and mathematicians tend to disdain, and for that I apologize. One of the biggest of those is that I put decorations on my vectors. If you look at our textbook, you will find that whenever a vector is mentioned, it is simply printed in boldface. And in most math classes, the decorations are completely left off when the instructor is writing the names of vectors on the board. So V with an arrow over it or just V by itself is the exact same thing. And so if you want to just leave your vectors alone, that's perfectly fine. If you want to put over arrows on everything and not worry about special symbols for unit vectors, that's fine. I'm going to become less and less useful about leaving those symbols on because the unit vectors we're dealing with later on are going to be kind of annoying. Um, but I wanted to at least mention that there is a culture war between mathematicians and physicists, and as a professor of math, I'm on the wrong side of the war, and I admit that very freely. Anyway, when we're talking about unit vectors, we generally call them E, but we're going to be looking at some specific unit vectors, which are called the standard basis vectors. The standard basis vectors are I hat, the vector 1, 0, and j hat, the vector 0, 1. And the way we have defined operations on vectors is, in general, if we have some c1 as a constant multiplied by the vector x1, y1 plus c2 as a constant times the vector x2, y2, then we will get the x component will be c1 times x1, c2 times x2. And the y component will be c1, y1 plus c2, y2. And that definition is really nice with my unit vectors, because if I have some x times I hat plus y times j hat, well, that's really just x times 1, 0 plus y times 0, 1. And by my definition of linear combinations of vectors, that's the same thing as x, y. So we can do operations. If I break down these two operations, we talk about vector addition and scalar multiplication. Again, anyone who is going on to take a course in linear algebra, you'll learn a lot more about the specifics of those operations in that course, or if you've already taken linear algebra. There's a lot of detail, a lot of specifics of how those have to work that I'm completely glossing over because I'm assuming that you have seen all of these ideas at some point in the past. Whether or not you have seen both the angle bracket component notation and unit vector notation is a little bit more up in the air. Very often, class will just choose one and stick with it. I wanted to at least mention both of them. Uh, for the most part, I'm going to be working with the unit vector notation in this course. I find that it's a little bit easier to deal with. as an example, let's consider finding the unit vector which points to the right along the line y equals square root of 3 over 3 times x. I'm not going to worry too much about drawing it to scale, but I do know that square root of 3 over 3 is a positive number which is smaller than 1. So the graph y equals root 3 over 3 times x looks something kind of like that. And so a vector which points along this line to the right, let's use the thicker ink so you can actually see it. A vector which points along this line to the right is going to look something like that. And so how do we figure out where this vector is? Well, we know we want a unit vector, which means that the magnitude of this vector is going to be 1. And one really easy way of defining a vector is based on its magnitude and its direction. So if we can figure out that angle theta, we have the direction. And once we have magnitude and direction, then we're in good shape. But wait a second. Remember back to the video on first-degree equations. That angle is the angle of inclination for the line. We defined that angle tangent theta equals the slope. And there's the slope right there. Tangent of theta is square root of 3 over 3. This is a first quadrant angle, so we don't have to worry about anything weird happening with arctangent. And if you remember your table of special angles, the angle whose tangent is root 3 over 3 is pi over 6. All right, so we're looking for a vector with a magnitude of 1 and a direction of pi over 6. Technically, that's enough, but we've been talking about component form and unit vector notation, so let's stick with that. Let's name this. All right, it's going to be a unit vector, and we tend to use the letter E to represent a unit vector. Right, that's not the constant E, which is why I really like drawing the unit vector hat whenever I'm talking about it. Right? Not the constant, has nothing to do with 2.71828. The unit vector E, which has an x component. X is r times the cosine of theta. So that'll be 1 times the cosine of pi over 6. And since that's the x component, we multiply it by the x component unit vector I hat. And then a y component will be 1r times the sine of theta, which is still pi over 6. And then we multiply that times the unit vector for the y component, j hat. Of course, sine of pi over 6 is 1/2. Cosine of pi over 6 is root 3 over 2. And we have that this unit vector is root 3 over 2 I hat plus 1/2 j hat. It's a little bit hard to see, but there's something kind of curious about the components of this particular vector. Like I said, it's a little bit hard to see because fractions are weird and fractions that contain radicals are really weird. But let's take a closer look at these two vectors. If I take my y component, 1/2, and I divide by my x component, square root of 3 over 2. Well, it's pretty obvious. You can multiply top and bottom by 2 to clear out the complex fraction, and then you have 1 over the square root of 3. And then you can rationalize by multiplying top and bottom by root 3, and you get square root of 3 over 3. Square root of 3 over 3, that was the slope of the line that I started with. That's not a coincidence. The ratio of the y component to the x component of the vector which points along the line is exactly always the slope of the line. And if you stop and think about it, that should make sense to you. That gives us a different way of approaching this problem. For this particular problem, it wasn't that bad because we had a nice exact value trig function here, but you know as well as I do that that usually doesn't happen. So if we had a similar problem, find the unit vector which points to the right along the line y equals negative 5/4 x. Well, once again, I'm not going to worry about graphing it very carefully, but I know that 5/4 is bigger than 1 and it's negative. So I'm going to have a line that looks kind of something like this, which means that my unit vector in question is going to be kind of something like that. And I could go through and I could figure out everything I need to figure out. It would work out. But instead, I'm going to just take inspiration from what I saw in that last problem. Negative 5/4. That's negative 5 divided by 4. Set the y component as negative 5 and the x component as 4. This is a vector which points along the line, just by reading it right off of the slope. Now, in this case, this is not a unit vector, so we have a little bit of work left to do. So let's go ahead and calculate the magnitude of this particular vector. And I could have given us much easier numbers to work with, but I didn't. That's okay. 4 squared is 16, 5 squared is 25, 16 plus 25 is 41. And there's not really anything you can do with the square root of 41. But if I take my vector and I divide by that magnitude, then I will be left with a vector which has a magnitude of 1. So it'll be 4 over the square root of 41 times I hat minus 5 over the square root of 41 times j hat. And by thinking about things that way and thinking a little bit outside the box, I was able to write down the exact value of the x and y components of the vector without getting bogged down in any triangle trigonometry shenanigans and without having to resort to a calculator and approximate values, which I know is only important in math class, but you're in math class, sorry. Right. With those ideas in mind, I'd like you to see, or I would like to see, if you can think about how to do this the other way. I would like you to find the equation of the line through the origin, which follows along the vector e hat is 1 over the square root of 5 times I hat plus 2 over the square root of 5 times j hat. Right. Once again, take a couple of minutes to work through that problem, see what you come up with, and I'll see you in the next video.